We're going to cover each of these topics one by one, but very quickly, as you'll see as we move forward. The first one thing we're going to look at is why use the HCM and HCS for your analysis. We'll go through and look at these other ones along the way. The questions are best methodology, the one that's most defendable, and can you do everything you want to do in the analysis that you have in front of you? Highway Capacity Manual, the 6th edition, and the Highway Capacity Software HS7 that implements the 6th edition is the culmination of the manual that's been around since 1950. So very defendable. It's research built, millions and millions of funding from the National Cooperative Highway Research Program and the Federal Highway Administration, all the way since about the early 80s through today. Beyond that, beyond the panels for the funding projects, reviewing every step of the research, the results are peer-reviewed by hundreds of subcommittee and committee members on the Highway Capacity and Quality Service Committee before it's finalized and published in the Highway Capacity Manual. HCS implements the manual directly. The McTran Center has been going to the Highway Capacity and Quality Service Committee meetings for over 30 years. Going to participate, of course, and many changes that come up or issues that come up come from McTran's users, because there's tens of thousands of users that might see something that all that review didn't catch, but not often. But it's maintained constantly. Every time the committee meets, you may or may not know this, but they meet twice a year. Once in January at TRB and once in the summer someplace else, and almost always approve something to change in the manual. So once something is approved, McTrans will update the software, post it on the website, email all the users, and you get the updated version within a few weeks of the actual being taken, whether it's at one of the 2 meetings or even votes online between meetings. Every methodology is implemented. Freeways and highways, whether it's a segment or facility. On a freeway facility, you can model oversaturated conditions because you're looking at multiple segments over multiple time periods, and that'll give you even delays and queues. Unsignalized instrument, 2-way stop control, always stop and go roundabouts, and now you can model the segments between the roundabouts. So you get a string of roundabouts or even a roundabout within a signalized arterial. Signalized intersections, including phase duration and multiple period analysis for signalized intersections, access points, and interchange ramp terminals for arterials. No other procedure does this. Alternative intersections were added in the 6th edition and multimodal. So you can look at pedestrian, bicycle level, transit level service along an arterial, the perfect tool to quantify the trade-offs when you're considering complete streets or road diet. The HCS does implement everything in the manual completely and faithfully. That also means that you've got all the details, every little nook and cranny is covered. But if the manual cannot do something, then the software cannot do something. The manual does something a little incorrectly, so does the software. But it's the best you can do with all the research and the peer review, by far the most defendable and accurate methodology and software implementation out there. Why is this multiple period analysis so critical? If you're modeling congested signals, first of all, you have to collect data correctly. Not everyone does. In fact, many, probably the majority do not. And then once you get the results, do you really look and see if they're reasonable? What the manual says, if it's a planning application, then okay, an hourly volume peak hour factor works. But if it's operational, which includes signal timing, design, traffic impact studies, optimization, it needs to be a multiple period analysis that overcomes the 2 dilemmas in the peak hour factor and also allows you to model unmet demand from period to period as it grows and dissipates over the AM and PM rush hours. The peak hour factor converts an hourly volume to a peak 15-minute flow rate, but it has 2 problems. One is if movements peak at different times, then you can't have peak hour factor by movement. So the manual now decided to have peak hour factor for the intersection. But what that does, that takes away your ability for those 3 movements coming out of the office complex that peak radically for one 15-minute period, where the other 9 movements don't. So if you get rid of the peak hour factor and look at multiple period analysis, you solve both of those problems. To make this work correctly, you have to be able to have unmet demand and get the initial queue delay. And to do that, you have to know what the arrival rate is, not just the stop bar count. You have to count the arriving vehicles. If you go out there and do a traffic count, I've just got this simple problem here. We're looking at one movement. The stop bar count tops out at capacity. In this example, 500. You can't get more across the stop bar than what the capacity is. But there may be more demand than there is capacity, BDC ratio greater than 1. So when you count the cars, you count the stop bar in the second column, but you see what happens in period 3. 500 crossed the stop bar, but 25 were there during this period but didn't make it. So the demand is not 500, it's 525. The next period you have 500 again, but wait a minute, 25 came from here, so only 475 new ones, plus 75 in the period demand. Your demand for that period is 550. You have to collect this unmet demand at the end of each 15-minute period in order to convert your stop bar throughput to actual arrival demand. To do that, you count the queue on each approach during the last cycle of the 15-minute period at the beginning of red. You don't want to count a queue that red generated. It's the beginning of red to count the unmet demand. That allows you to compute the demand over here, which is the yellow curve, and you can see it's different than the blue curve. Now, this is the VDC ratio of 1.2. If it's 1.5, 1.7, this yellow curve would be way up here. And quite a difference in demand versus stop bar count. McTrans has a tool. It's an app that'll go on your computer, your phone, your tablet. You see it in the lower right here. You can count turning movement counts each 15 minutes, just like you do with any count tool. But at the end of the 15-minute period, it allows you to populate this unmet demand. It also allows you to count those other things that you need besides just vehicle counts to modify saturation flow, like heavy vehicles, pedestrians, bicycles, stopping buses, parking cars. All those kinds of things can be counted at the same time. Then when you're done, you save the file. The little program does this math for you and saves the arrival demand. And it all comes into HS automatically populating the multiple period analysis even before you put in the rest of the data. If you look at this graphic on the left, that's the capacity manual's version of why you need initial queue delay, D3 delay. The bracket over here says if you don't get unmet demand, this is going to be your final answer. If you do, this might be your final answer with initial queue delay thrown in. Now let me remind you what initial queue delay is. If I show up in fourth period and I'm the very first vehicle, I actually am the 26th vehicle because these 25 cars are sitting there waiting on me. The extra delay, these 25 cars, the unmet demand from the third period becomes the initial queue for the fourth period. That extra delay causes me is initial queue delay. When the VDC ratio gets up around 1.5, look at the difference. If you do this incorrectly, you're going to get about 100 seconds of delay. That's what you get when you have a VDC ratio equal to 1. But if you do it correctly, you're going to have 372 seconds of delay. That's very different, which is correct. Think about that congested signal you went out and you counted cars for. When it's 1.5 VDC ratio and it's congested, how many cycles does it take the vehicle to get through? And it's 2 or 3. You got 2 or 3 long cycles in a peak period. That's over 6 minutes. That's nowhere near 100 seconds. You're underestimating it dramatically when you get to 100 seconds. Same thing with queue. A 10 vehicle queue done incorrectly is a 23 vehicle queue done correctly. So what you don't want to design a left turn bay for 10 cars when 23 are going to show up. This also impacts timing, everything else that you do. So what I always tell people is always run a multiple period analysis. If it's unsaturated, it won't matter. You just overcome the peak hour factor dilemma, but you don't have unmet demand. If it is, then you have to have this unmet demand shown. So one thing I also tell people is that if you're reviewing somebody's work and they say, oh, yeah, I counted the unmet demand, what you really want to ask for is, show me this data. If they don't have this data, they may not have counted the actual demand. So why do you care? Just like I said, turning lanes might be done incorrectly. If you optimize something based on 100 seconds of delay, you get a 120-second cycle, and you get certain splits and offsets. If it has 372 seconds of delay, you're going to get much longer cycles. Splits and offsets will be different. It makes a difference. What if you did a traffic impact study? You do it incorrectly, they mitigate 100 seconds down to 70, costs the developer $100,000. Do it correctly, they mitigate 372 seconds down to 100 seconds, it costs the developer $1 million. If you do it incorrectly, the city ends up eating the other $900,000 and paying to fix it after the developer kind of got away with it. So lots of different things besides doing things incorrectly so the road user has more time and fuel expended. Why use HCS to optimize? HCS doesn't get the credit it deserves for optimizing signal timing. If the congested signals on the arterials, are they modeled with multiple period analysis? If they're not, then the optimization is not going to work, just like I said. Using the flow profile as adjusted by access points, and can you include interchanges and alternative intersections which are modeled differently within your process? The multiple period analysis is in the HCM and HCS procedures. Phase duration model predict the average phase over the 15-minute period through the multiple cycles where it varies by cycle for actuated movements. All the saturation flow adjustments are there. The flow profile is used, as well as the access point effects on the flow profile that I'll show you in a few minutes. You could also have an arterial with 15, 20 signals, and 2 of them happen to be in an interchange. That's modeled differently. So you can embed the interchange within the arterial, whether it's a diamond interchange, a SPUI, a DDI, or 6 different flavors of partial cloverleafs. The same is true for alternative intersections. You could have a DDI, you could have a displaced left turn, you could have a R-cut or super street, you could have an MUT intersection, also could be factored in and included in that arterial. So now you're optimizing using the ACM procedure with all these things built in. So you're not modifying the procedures whatsoever. You're just using a genetic algorithm to eventually converge on the best solution. And you can ask it to give you the best cycle length, splits, offsets, any of the above, all of the above. You can use overall delay, arterial delay as your objective function. That's what's most common. But you might care about level of service of travel time, even stops. If you're modeling for an AM peak and 80% of the traffic's going the forward direction in AM peak, then you can give it 80% of the priority by changing that number right there. Lots of good reasons to use HCS for optimization. What about access points? I brought that up a couple of times. If you understand the flow profile procedure, then you'll understand the access point interference. Even if you drive, you can tell the difference. Suppose you're leaving this signal here and you're driving down the road and you get up to 40 miles an hour, you're in the rightmost lane, the car in front of you decides to turn into the side street. He slows down to 10, you have to slow down to 10 because he slows down to 10. So you're delayed. And the car in front of him keeps going. So now there's a gap between you and the car that's now in front of you after he turns, and you've slowed down. So the overall platoon between the signals, speed is reduced for all the access point activity and broken into pieces, decayed because of the access point activity. What does that really mean? Here's the flow profile. If I have this movement up here, and I want to know what happens when it gets down here, in this perfectly timed pair of signals, this is it right here. All the southbound through up here arrive on green downstream. The side street left is protected. You can tell it's a protected left because it comes down the road as a platoon and it arrives at the end of the green. And then the right turns come more randomly and they arrive here. But what happens when you have a bunch of access points in here is it slows the platoon down, which means this leans. and it ends up falling a bunch in the red. It also breaks it into pieces. It's no longer contiguous like this. It wrinkles like this, further putting more traffic into the red, arriving on the red. So again, optimizing with this included in the process gives you much better field results than pretending the time-space diagram is correct, which it's not. So why attend training? To me, sometimes you think about, well, I'm using software. It knows what it's doing. I'm not sure I have to know all the details, but the more you know, the better you code data, the better you read the results when it comes out. And the more you know what's important when you model something like access points and phase duration and all these things that maybe you ignore it sometimes. Again, back to the credibility of the research-driven, peer-reviewed HCM and the faithful implementation of the software and how well it's kept up to date. Again, no other package doing this. Every analysis is implemented, and there's so many steps in between. The more you know, the better your analysis is going to be. Every little piece is cumulative and ends up with the best results, the better informed you happen to be. So the highway capacity software implements everything. We've gone through this list before. Federal, you can do it freeways and highways, stop control, roundabouts, excuse me, signalized intersections, urban streets, even the phase duration model. The interface covers every one of these things. And in streets, it actually combines signals, arterials, the segments and facilities with interchanges, alternative intersections able to be mixed in where appropriate. All levels of stop control or roundabouts, including the segments between them. If you have something that the manual cannot do, the two biggest examples are queue spillover and free rights. The HCS is now connected with Transmodeler. What the manual says to do when there's a limitation is simulate it. You want to simulate it in a simulation tool that is HCM compliant, that makes the simulation tool think like the HCM as much as possible so that level of service can be applied. You click a button, you take the queue spillover, you send it that approach to Transmodeler. It computes the effect of the spillover on the adjacent through where the HCM is ignoring it. You then come back to HCS, modify a few things to make that also true in the HCS run. Same thing with a free right. The exclusive right turn lane that's unsignalized at a signalized approach, where it has a triangular island and it enters a cross street with a yield or stop sign. The manual now says that delay can be included in the average for the approach and intersection, which it should be, to be able to show the benefits of having the free right, but it doesn't tell you how to compute the delay. Again, a click in the Transmodeler, it computes the delay. It's a gap acceptance procedure. You code it into HCS, you're done. Everything else that you can do in the manual, you can do in the software, including the highway safety manual module, signal warrant from the MUTCD, and that little tool I showed you a little while ago. So that's it for the topics. I'm going to let this stop now and close it out live. Thank you.